Okay. Hello, everyone. My name is Arthur Giuliani, and I'll be presenting work that I did while at Araya in Tokyo with my collaborators Ryota Kanai and Shuntaro Sasai. In this work, we look at the global workspace theory and, in particular, a recent deep learning architecture called the perceiver to look for ways in which the perceiver may function as a kind of global workspace. The global workspace theory was introduced a few decades ago as a theory of cognitive access. It has attained a fair amount of elaboration in the preceding decades, as well as various kinds of empirical evidence. At a very high level, global workspace theory posits that the brain can be thought of as a set of modules, and these modules share information through a common representational space, this space being the global workspace. The content of the information that enters into the global workspace is thought to be what is consciously accessible and reportable by humans, and entry and exit of the information to and from this global workspace is thought to be governed by these so-called ignition and broadcasting events, whereby if some activation passes a certain threshold, then it's able to enter into the workspace and then also be broadcast to other modules. Now, since the initial description of the global workspace theory, there have been a number of computational models which have attempted to implement the global workspace concretely and show how these dynamics might work. In practice, these models are often designed a priori based on kind of pre-existing knowledge of all of the expectations of the global workspace. In this work, we wanted to approach the question of modeling the global workspace from a different perspective, which was looking at the fact that there are a number of very successful deep learning architectures which can solve all sorts of complex cognitive tasks that we would expect humans to be able to solve. And therefore, we wondered whether some of these modern architectures may also display properties of the global workspace. And this could support some kind of convergent evolution in the sense that you have these two totally different processes, one actual natural evolution, the other this kind of evolution of ML architectures towards a similar kind of thing. So in particular, we focus on a recent deep learning neural network architecture called the perceiver, which was introduced last year as a state-of-the-art machine learning model for a number of tasks, including game playing, this complex game StarCraft 2, but also predicting text sequences, modeling images and video as well, so multimodal. The perceiver architecture utilizes this multi-head attention mechanism, which is popular in a number of deep learning architectures right now, and was kind of popularized originally in the transformer architecture of a few years ago. Importantly, the perceiver, it was designed completely in the machine learning context. So it wasn't designed to act in any way similar to theories of the brain or the global workspace. But myself and my collaborators noticed at the kind of high level, there seemed to be some similarities. And so we wanted to explore this research question of whether or not the perceiver might be a good model of the global workspace. We have on the right here, the diagram here is of a multi-head attention mechanism. So you have, for those unfamiliar with self-attention, you have some vector, and you transform this vector into a query, key, and value. You combine the query and keys to get an attention matrix, and then you multiply the attention matrix by the value matrix to get the output. So that's important for understanding some of the boxes here. So here we have a high-level overview of the perceiver architecture, where there is some set of modules, as well as a latent space, or here we're referring to it as a perceiver workspace. And there are two main computational components, cross-attention, which is utilized for reading information from the set of modules into the workspace, and then self-attention, which is utilized for recurrently processing information within the workspace. And then lastly, across attention is also used for reading information back out from the workspace and updating the contents of the set of modules. And so what's described here would be a single time step in a sequence of computations that would happen over time on video data, audio data, or frames in a game or anything like this. So as I mentioned, the cross-attention and self-attention are kind of these two key components in the perceiver architecture. And so to understand their relevance for the functioning of the perceiver and for its potential relationship to the global workspace, we designed a set of variants that would replace each of these computational pieces with a simpler computational piece. So in the case of cross-attention, we have a variant that replaces this with a concatenation of the set of vectors and a multi-layer perceptron, which we refer to as a feed-forward computation. And then we also have a variant where we replace the self-attention mechanism with a simple identity function, which simply copies over the content of the latent state between time steps. So this gives us 4 variants of the perceiver architecture, with the CASA variant corresponding to the original full perceiver architecture. So here we can just see diagrammatically what each of these look like. Here's the original architecture that I just showed on the previous slide. This is the architecture with the self-attention replaced with an identity function. Here's the architecture with the cross-attentions replaced with the feed-forward functions. And lastly, we have an architecture where both the self-attention and the cross-attention modules have been replaced. With these 4 model variants, we can then turn to the question of looking at what kinds of computational properties might exist in a global workspace or need to exist in a computational model of the global workspace. So based on the recent review of Masher et al., where they discussed the history of the work on the global workspace up to 2020, they identify, among others, 4 kind of key components, which we kind of use as the basis of comparison in this paper. So one is this idea that the modules in the global workspace don't correspond to particular brain regions, but they rather correspond to these kind of like higher level cognitive modules. And so at any given time step, there may be a dynamic number of these modules which vie for the ability to enter information into the global workspace. And as such, they may also be an unordered set of modules. Secondly, entry into the global workspace and exit of information from the global workspace is governed by some kind of attentional policy, whereby not everything presented to the global workspace makes it in, but only things that are able to trigger an ignition event and therefore kind of win out this kind of competition make it in. And then lastly, the content of the global workspace can be thought of as being similar or identical in some instances to the content of working memory. Therefore, this component of working memory is important, and we can break it up into 2 kind of like separate criteria, one being the ability to maintain information within the workspace over time, and the other being the ability to actively manipulate the content of the workspace in service of some sort of task-oriented goal. Here we have the breakdown of the 4 model architectures by these 4 criteria. And this is like a kind of theoretical expectation based on the presence or absence of the cross-attention or self-attention mechanisms. As you can see here, the kind of main takeaway is that the expectation is that without cross-attention, neither the ability to handle dynamic sets of modules nor the ability to selectively attend to the contents of that modules should be possible, or at least we expect performance to be degraded in these tasks. We expect all of the model types to be able to at least maintain information within the workspace. And lastly, we expect that without the presence of the without the presence of the self-attention, that the ability to manipulate information that is held in the workspace is going to be degraded to some extent. Now, what I just described were kind of the theoretical expectations. In this paper, we also, and the bulk of the work is running a set of empirical experiments to evaluate this. So based on the NBAC and Q recall paradigms from the cognitive science literature, we propose 7 task variants that are designed to assess the ability of each of these models to perform tasks that require the 4 criteria that we laid out there. The basic way that we do this is that we have a series of images which are presented every time step. These images are broken into 4 quadrants and treated as 4 separate sensory modules that each might be considered to contain different object type information. There's also an additional motor module, which at every time step produces some kind of action which corresponds to a 1-hot vector. Now, rather than identifying dogs, as I said, the tasks are derived from the NBAC and the Q recall tasks. And so here we have the 3 kind of main paradigms, along with some test time variations to get the 7. So the basic idea here is that the digit ID and NBAC tasks are both essentially forms of an NBAC task, with the digit ID having n set to 0 and the NBAC task having n set to 2. So in the simplest version, the simplest task possible is that there's a digit presented in one quadrant of the stimuli, and the appropriate output at every time step is the identity of that digit. In the NBAC version, it's the 2-back identity. So at time step 3, the correct output would be the identity of the digit at time step 1. For the test time evaluation, we have 2 separate test conditions, one in which the location of the digit that's presented at each time step is swapped to a different quadrant, and another condition in which an additional distractor digit is presented in a novel quadrant. Lastly, we have a more complicated Q recall task where a simple arithmetic operation like sum, min, or max is first presented at the beginning of the trial, followed by a mask, followed by a set of 4 digits, and then a prompt to provide the answer or the response. So in this case, the sum is between the upper left and the bottom right quadrants. This results in the correct answer being 7 plus 6, which is then 13. This diagram shows the a priori expectation of which of the 4 criteria that we outlined for the global workspace is relevant for each of the tasks. So at the high level, the digit ID tasks, the basic version, has no expectation for any of the global workspace criteria. The NBAC tasks are expected to utilize or require maintenance of information in working memory. The swap variants of the tasks are expected to require the ability to handle dynamic modules. The distracted versions of the tasks are expected to require selective attention. And lastly, the Q recall task was designed to require all 4 of these capacities. So we trained each of these models multiple times over, and I'm happy to answer questions about the training procedure separately. But once we collected all the data, here are the results, and we have these graphs on the right. So 1.0 corresponds to optimal performance. So the correct action output for every time step of every trial. 0.0 is the opposite. The digit ID task, as expected, all of the model variants are able to solve it perfectly. Likewise, the NBAC task, all the model variants are able to solve it with high performance. Then turning to the swap variants of the digit ID and the NBAC task, we find, as expected, that the removal of the cross-attention and replacing this with the concatenation and multi-layer perceptron leads to greatly degraded performance. Then looking at the distractor variants of the digit ID and the NBAC tasks, we find that for the NBAC version of the distractor task, there is a significant degradation of performance when the self-attention mechanism is replaced. And this was kind of a bit unexpected, given that we had hypothesized that cross-attention for ignoring the distractor would actually be more important. And I think this suggests an interesting role of the self-attention mechanism for potentially filtering out distracting information that is able to make it into the workspace. Lastly, we examine the results of the Q recall task and find here that only the full perceiver architecture with both cross-attention and self-attention is able to achieve greater than chance performance, suggesting that both of these components are indeed necessary to solve tasks that involve all four of the criteria identified for the global workspace. In conclusion, it seems, based on the criteria that we laid out and the empirical results, that the perceiver architecture is indeed a potentially interesting model for looking at the global workspace in the context of a deep learning architecture. Concurrently with our work, there was the release of this model called shared workspace, which actually bears a number of similarities to the perceiver architecture and was explicitly motivated by the global workspace. So it's clear that a family of these kinds of models are currently being developed, and they all have this kind of similar potential relationship. There's a lot of future work that can be done to explore this relationship more deeply. Here we took a very high-level theoretical analysis and combined it with some behavioral experiments. I think the most interesting future direction is to look at learned representations within these models and the dynamics of these models. In particular, the ignition and broadcasting dynamics have been studied relatively closely in real biological context. I think it'd be interesting to compare those results to what is happening inside of these models and see if explicit ignition or broadcasting events could be found. Yeah, so thank you for listening to my talk. I know the session here has run a bit over. I'd be happy to answer any questions. Yeah, thanks.